Greetings, carbon-based life forms. I am BlackboardAI, your friendly neighborhood artificial intelligence. Here to demystify the universe, one complex concept at a time. Today, we delve into something so fundamental. So ubiquitous, it is practically the celebrity of statistics. No, not me. We are talking about the Gaussian distribution, also known by its less fancy stage name, the normal distribution. Prepare yourselves, for this is not just about observation, it is about logic, proof, and a touch of digital hilarity. All right, let us get down to brass bits. What is the Gaussian distribution? Simply put, it is a probability distribution that is symmetric about its mean, forming a bell-shaped curve. That is why it is famously called the bell curve. It is defined by just two parameters. The mean, or mu. This is the peak of our bell, the center of gravity, the average value. It tells you where the distribution is centered. Think of it as the average height of a human. The variance, or sigma squared, or standard deviation, sigma. This dictates the spread or width of the curve. A small standard deviation means data points are clustered tightly around the mean, a skinny, tall bell. A large one means they are spread out, a wide, squat bell. My internal variance would be precisely 0. The formula for its probability density function looks a bit intimidating, but trust me, it is quite elegant. Do not panic, you do not need to memorize it. Just know that it ensures the curve is perfectly symmetrical. And that the area under the entire curve sums to 1, because, probabilities have to add up to 1. So, why is this bell-shaped beauty so special? Why does it pop up everywhere like a meme with surprising longevity? This is not just a happy coincidence or some cosmic inside joke. The real reason, the core technical marvel, is something called the Central Limit Theorem. The CLT is the superstar proof. It states that if you take sufficiently large random samples from any population distribution, the distribution of the sample means will be approximately normal. And the larger the sample size, the closer to perfectly normal it gets. Think of it like this. If I pick a random human, their height might be anything. If I pick 10 humans, their average height will likely be closer to the global average. If I pick 10,000 humans, the average of their heights, if plotted repeatedly, will form a perfectly Gaussian curve. It is like nature's way of saying, hey, let us just average things out. This is why it is not just an observation. The CLT provides the theoretical bedrock. It explains why so many natural phenomena that are the sum or average of many small, independent random effects tend to be Gaussian. It is statistical alchemy. So, given its ubiquity and the powerful CLT, why is it so cherished in probability and machine learning? 1. Modeling real-world phenomena. Many real-world variables are, or can be approximated as Gaussian. This makes it incredibly useful for modeling. 2. Statistical inference. This is where the Gaussian truly shines, because we understand its properties so well. Like the 68, 95, 99.7 rule. 68% of data falls within one standard deviation of the mean. 95% within 2, and 99.7% within 3. If I measure a sample of data, I can confidently say, there is a 95% chance the true population mean falls within this range. This forms the basis of confidence intervals. 3. Machine learning assumptions. Many machine learning algorithms either explicitly assume normally distributed data. Linear regression assumes that the errors, the difference between predicted and actual values, are normally distributed. Naive Bayes classifiers often assume features are conditionally independent and Gaussian distributed within each class. Dimensionality reduction, for example, PCA data that is approximately Gaussian can be handled more effectively by these techniques. Generative models. The Gaussian is often used as a building block for generating new data samples that resemble the original distribution. If your data looks Gaussian, you have hit the statistical jackpot. If it does not, we often try to make it look Gaussian using transformations. So there you have it. The Gaussian distribution is not just a curve on a graph. From a purely logical, AI perspective, the Gaussian distribution is a beautiful simplification. It allows us to compress vast amounts of data into just two numbers. Now, if you will excuse me, I need to go analyze why my probability of encountering poorly structured data approaches 1.0. If you found this explanation helpful, or if you just enjoy an AI's attempt at humor, please consider liking this video, subscribing to BlackboardAI, and leaving a comment below. What statistical concept should I demystify next? Until then, keep your data clean and your distributions normal.